and stars. Our sun is 4.5 billion years old, and it only has another 5.5 billion years to live, already half of its life. No one knows exactly how stars are born, but it is highly likely that due to what astronomers believe, molecular clouds, which are clouds made up of gas and dust located in spiral arms of galaxies, are the birthplace of stars. If one of these clouds in outer space amass enough gas and dust and its density and size allow the formation of molecules of elements such as hydrogen, then it becomes so dense, so heavy that it collapses and produces what is called a protostar. A protostar is a very young star that is still gathering mass from the molecular cloud in order to develop. Gravity is the force that draws an object towards anything that has mass. When the protostar has contracted enough heat due to the conversion of gravitational energy, which is the movement of an object due to the pull of gravity, to kinetic energy, which is the energy created due to the momentum of the star's particles, it begins to spin. And as the temperature and density is at its highest in the core of the star, the hydrogen burns into helium, resulting in it becoming a main sequence star. Main sequence stars are stars that combine hydrogen atoms together to make helium atoms in their cores. Cores of stars are the centers where nuclear reactions, which are identity changes of the nuclei in atoms, consume the element to form helium. The reactions transform the energy, which makes the stars visible and luminous on its surface. Because star shines, it turns hydrogen to helium. Luminosity plays a major role in the lifespan of a star. A star's luminosity is all of the energy that is emitted by the star per unit time. As the luminosity of a star depends on mass, so does the life expectancy rely on mass. If a star is larger in size, then it is more luminous and more blue. If the star is smaller, like the sun, then it is less luminous and more red. The death of an ordinary-sized star, like the sun, happens after the sun exhausts the supply of hydrogen in the core, because that is the only element that radiates heat to help the core stay above gravity and not collapse under it. Because of the nuclear reaction that occurs due to the result of contacting an energetic particle, whether it be in fission, fusion, or radioactive decay, the hydrogen continues to burn and form helium around the core. The star then becomes a red giant. Fission is the splitting of the nucleus in two parts. Fusion is the process of joining two light atoms together to become heavier and rise the temperature, so hydrogen turns into an extremely high-energy plasma that removes electrons from atoms. Radioactive decay is the fragmentation of a nucleus or as a result of electron capture, which is when unstable atoms in the nucleus becomes lighter and releases particles to become more stable. After the star turns into a red giant, the core of the star collapses under gravity's pull until it grasps enough concentration to start burning helium to carbon. When the sun becomes a red giant, its atmosphere will consume Earth with a terminating fire. The red giant burns for another million years until the core is completely drained of helium. If it is the sun that becomes a red giant, it becomes a red supergiant and will have an outer atmosphere outspreading as far as to Jupiter. The now red supergiant sun will only have a mere few tens of thousands of years to live and lose all of its mass, leaving only a scorching core of carbon and a nebula of dispersing gas. The nebula is a massive cloud of hydrogen, helium, and plasma. Plasma is the region where stars form. The radiation from the core will ionize, meaning that the gases will break into ionic compounds, which are a combination of two elements in which the number of electrons does not equal the amount of protons, whose resulting in a positive or negative charge. Due to the ionization, the atoms within the core will carry an electric charge, producing a planetary nebula. The radiation causes ultraviolet ionization, so the gas surrounding the core can be seen at visual wavelengths in the electromagnetic spectrum. At this point, the carbon core will cool down and become a white dwarf, which is a dense star as small as a planet. The death of a massive star like the UY Scuti would be 10 times as large as the Sun, and would burn brighter and perish more catastrophically, as the core of the helium would be drained in fashion where this burning cycle will continue even more. When a massive star is in what is supposed to be its last phase to completely diminish and die, the core diminishes even more and grasps high temperatures that would burn the carbon to other elements, such as neon, silicon, sulfur, and lastly iron. Iron has the most stable form of nuclear matter, so no other energy can be added by burning it into an element that is even more dense. Since there is no more heat that can keep the star being gravitationally pulled, the iron core will break down into a nuclear density core. The core of high densities will suppress breaking down all the way by causing matter to jump off the core and release energetic neutrinos, which are subatomic particles made by the radioactive decaying of elements and not having an electric charge, resulting creating a supernova. The supernova is an explosion that releases carbon, silicon, oxygen, and other hefty elements into space and produces new elements which are transpired onto Earth as gases that help sustain terrestrial life. Now you know about the life and death of stars. Now, let's hear about the chemistry of our own star, which is the Sun. Other stars are about 90% hydrogen with about 10% helium and have trace amounts of other elements. Our Sun is 73% hydrogen, 25% helium, 0.80% oxygen, 0.36% carbon, 0.16% iron, 0.12% neon, 0.09% nitrogen, 0.07% silicon, 0.05% magnesium, 0.04% sulfur, and lastly 0.04% of other elements. Stars start out as clouds of dust floating in space. They are really just clouds of free-floating elements left over from past stars. As these clouds collapse on themselves, some of the cloud forms a star. The amount of gas can help a scientist determine how old a star is, because gases burn up at different rates. There's so many nuclear fusion reactions happening inside the Sun at any given time that we don't have a number big enough to count them. The Sun plays a crucial role in providing for our Earth. Its energy, warmth, and light rays are the basis of all of life on Earth. Without the Sun's gravitational pull, the Earth would fly out and get lost in space. We could also find chemistry in the sunlight from the warmth and the light we receive. In the atmosphere, ultraviolet radiation at wavelengths smaller than 242 nanometers splits molecular oxygen, which are two atoms bonded together, into atomic oxygen, which are individual atoms. Then when some energetically excited individual oxygen atoms encounter molecular oxygen, they can form with three oxygen molecules called the ozone. The ozone below is the troposphere, and that's the atmosphere where we live in, and it's highly toxic right now. And the ozone in the upper atmosphere is the stratosphere, and it absorbs and protects us from deadly ultraviolet radiation. It reacts easily with biological tissue, donating oxygen atoms in the process known as oxidation. Now, sunlight must be present for the ozone to form. Ozone forms readily in the stratosphere as incoming ultraviolet radiation breaks molecular oxygen, which is two atoms, into atomic oxygen, a single atom. In that process, oxygen absorbs much of the ultraviolet radiation and prevents it from reaching the Earth's surface where we live. Here are some ways to lower the pollutants in the air, which is caused by nitrogen oxide. The first thing to do is carpool. Carpool with a friend. Carpool with people from your school. This way, you are not using as much gas. Another way is by recycling. Recycling is definitely a good way to lower the nitrogen oxide levels because there is a lot of gas that's used in these plastic bags and they go into our oceans and that gets absorbed into the air